welcome to another triple physics lesson. We're on lesson 3 of seismic waves today, and we're talking about locating earthquakes. Our keywords for today are lag time, triangulation, and epicenter. And we've got 4 questions for our do now, so I need you to go ahead, click pause, and complete those. Okay, our answers then. Name the 2 seismic waves that are longitudinal. That is P waves and surface waves. State the 2 uses of the shadow zone. Number 1, it proves the outer core is a liquid. And number 2, it's used to calculate the size of the outer core. Number 3, explain the origin of the shadow zone. Well, if you remember, the shadow zone is an area where S waves can't be detected. So S waves cannot pass through the outer core because it is a liquid. This means there is an area of the Earth that cannot detect S waves following an earthquake. And finally, order the seismic waves from slowest to fastest. So we start with surface waves, then S waves, and finally P waves. So make sure you've got all your correct answers and click pause if you need to. Okay, our naughty words for today. We're going to explain how the epicenter of earthquakes is located using lag time and triangulation. Our learning journey then is we're going to define the term lag time. And then secondly, we're going to explain why 3 earthquake detectors are required to locate the epicenter of an earthquake. So our first thing then is, what is this thing called lag time? Now, lag time, believe it or not, is how, and it's quite a simple way, how all seismologists, scientists studying earthquakes, calculate how far away an earthquake is. And you can see down at the bottom here, I've got a seismogram. Okay, I've left the surface waves off because I don't want to confuse those, but I have got a seismogram. Now, what you will notice is that along the bottom of that seismogram, I have got a time. On the left, it starts at 6:30 a.m. and it gets up to 6:44. Now, we know that P waves are called primary waves because they're fastest and they arrive first, and S waves are called secondary waves because they are slower and they arrive second. And this is shown on our seismogram. If you look carefully, my P waves arrive at around 6:35, okay? And then we have, for about a minute, we've got some P wave activity. And then we've got no real earthquake activity, okay? It's called background noise. In other words, just the general vibrations of the earth, okay? Then at 6:39, our S waves begin to arrive. So between 6:35 and 6:39, no S waves were detected. And we call this the lag time. Now, this lag time is used to work out how far an earthquake is away. It's not able to find out the exact location, but it can work out how far an earthquake is away. And the longer our lag time, the further away the earthquake is. And what I want you to think of here is, imagine that you are in a race with Usain Bolt. Okay? Now, if you run 100 meters against Usain Bolt, he's probably going to finish 20 meters in front of you, isn't he? Or 2 seconds before you. So that's the lag time. Whereas if you run a longer race against Usain Bolt, the lag time is going to be different. If you run 400 meters against Usain Bolt, rather than arriving 2 seconds after him, you're probably going to arrive 8 seconds or 10 seconds. So this lag time, the longer the lag time, the further away the earthquake is. Now we're going to have a quick review on lag time. We've got a multiple choice quiz. So review 1, question 1. Now, again, we've done this before. Oh, I've made a little typo there. Let's change that. If you're doing this in your book, you can write question 1, ABC, or as many people have been doing, you can change the colour on your computer. That is fine. So question 1. Following an earthquake, a seismogram detects A, both S waves and P waves at the same time, B, S waves before P waves, or C, P waves before S waves. Following an earthquake, a seismogram detects A, both S and P at the same time, B, S before P, or C, P before S. Question number 2. The difference in time between the arrival of P and S waves is called A, lag time, B, wave delay, or C, wave lag. Question number 3. The difference in time between the P and S wave arrival is used to A, find a location for the earthquake, B, calculate the magnitude of the earthquake, or C, calculate how far the earthquake occurred from the station. So what do we use that difference in time for? And finally, a bit of like an exam style multiple choice question here, challenge multiple choice. I've got 3 earthquake stations which you can see on the diagram. I've got Tokyo at 4,100 kilometers, Hawaii at 11,000 kilometers, and Hong Kong at 1,958 kilometers. Which station will have the longest lag time following the earthquake? Is it A, Tokyo, B, Hawaii, or C, Hong Kong? Now you may want to press pause at this point if you want to have a think. But we are going to look through the answers now. Okay, question 1. Following an earthquake, a seismogram detects P waves before S waves. Remember, our P waves are called primary waves because they always become first. Question number 2. The difference in time between the arrival of P and S waves is called A, lag time. If I quickly go back to our seismogram, that blue time there, that is our lag time. Okay, that difference. Question number 3, the difference in time between the P wave and S wave arrival is used to C, calculate how far the earthquake occurred from the station. Remember, we can't find the location exactly with one station, and it's not used to calculate the magnitude of the earthquake. And finally, for question 4, out of our 3 stations, Hawaii will have the longest lag time because it's furthest away. Okay, so we've learned about lag time and how lag time can tell us how far an earthquake is away. But now we're really concerned about where exactly that earthquake happened, because it's all well and good knowing that it happened 1,000 kilometers away, but we're not going to go to every town which is 1,000 kilometers away and try and find out which town had that earthquake. So to do that, we use something called triangulation. Okay, so we use triangulation to work that out. That's our process. And triangulation is shown in the diagram at the bottom. I've got earthquake station A, B, and C. Now, A, B, and C have all detected how far away that earthquake has happened. So for A, the distance is on their blue circle. For B, it's on the red circle, and for C, it's on the green circle. Okay, so each station has generated a radius of how far away it could happen. So for C, it could be anywhere on that one there. So we can't just detect it with one station because it's only showing me the distance. Now, you may be thinking, well, why wouldn't 2 be good enough? To explain why 2 can't show you an exact location, it's much better than 1. But if we look at the line for B and C, you will notice that B and C cross where the star is, and they cross lower down. There's a red and a green light crossing. So from those two readings, we're able to find out two locations. But again, that's not that good, is it? Because if you had a location and they say it could be in Cardiff or Swansea, you really want to know which city had that earthquake. So we need three. And the point where our radius or our distances all intersect is where that epicenter is. And there is only one point where all three circles will cross at the same time. And that is what we call the epicenter, or the center of the earthquake. And it is shown by that yellow star. Now, often, and obviously in the world, there are more than three earthquake centers. So often they will use more than three, just to make sure perhaps that there's been no inaccuracies or mistakes made whilst finding those distances, okay? Because that could be really bad. You could send all your police, all your ambulances, all of your firemen down to Swansea when you need them to be in Cardiff, if there's a mistake. But again, so one only tells us how far it could be. Two circles will give us two locations, and three circles intersecting will give us that magic epicenter which we want. So our final review activity for this lesson, you've got 5 questions. Okay, I need you to press pause and complete those questions now. Okay, our answers. Question 1. Name the process used to identify the epicenter of an earthquake. That is triangulation. Okay. Question 2. Explain why one station cannot identify the exact position of an earthquake. Well, if you remember, we said one station, it gives us a radius. It can only show how far the earthquake is from them. Question number 3. Explain why using the data from 2 stations provides 2 possible locations. And to think back to this, where our circles for B and C, because the possible radius lines intersect twice. Question number 4, explain why 3 stations can show the exact position of an earthquake, because all 3 lines will only intersect at the same point once. So remember, that magic golden star, that is where my green, red, and blue all cross over together. And finally, suggest why seismologists often use data from more than 3 stations when locating earthquakes. And a reason for that is, as we said, to make sure there have been no mistakes, eliminating any inaccuracies. So make sure you've got those answers correct. If you've got any questions, email a member of the science department, and I hope you have a good rest of the day. Thank you.